Welcome back. So in the first video, we kind of practiced how to view compositions of two functions. I've got another example at the bottom of the screen here. I would like to view the function y equals the x squared plus 1 all to the fifth. I would like to view that as a composition and call it f of g of x. And in the last video, we kind of rehearsed decomposing this into the f of x and g of x, or f and g. Now, I'd like to introduce and use the variable u in addition as a label. So I would want to think of this as y equals something to the fifth. I'm going to call it u to the fifth, where then we define u to be x squared plus 1. So if I write it that way, you notice that y is a function of the variable u, and u is a function of the variable x. But if I combine them by directly substituting x squared plus 1 for u, you could think of y as also just a function of x, because that's what I've got over here. This is all just a function of x. Okay? Now, let's read the chain rule for the first time. And it says, suppose we have a function defined this exact way. Y is a function of the variable u, such as what I've got here. U is a function of x, such as I've got there. But now I'd like to find dy dx, the derivative of y with respect to x. Which in my example would be to find the derivative of this big expression over here. Okay? Now, the chain rule basically breaks this down into two parts. And it requires that we decompose this into its basic components. Y is a function of u, and u is a function of x. And all the chain rule says is, once I have that breakdown, I just find each of those derivatives with respect to their variables, and then multiply them together. It says take the derivative of y with respect to u. So in other words, on this side, I would find the dy derivative of y with respect to u, which is just the basic power rule where the variable is u. So 5 u to the fourth. And then multiply that by the derivative of u with respect to x. If I think of u as a function of x, I could call this the derivative of u with respect to x. And that would be the basic power rule, or so forth, 2x plus 0, or just 2x. And the chain rule says that once I've done that, multiplying those together gives me the derivative of the original big expression. So according to this, I'm going to take the derivative, 5u to the fourth and I'm going to multiply by 2x. Okay, because what's happening there is I'm taking dy du times du dx. So I'm taking this derivative times this derivative. Now, it makes no sense in the answer to be in terms of both u and x. So what I'm going to do now is just I'm going to replace u with what I said that was equal to. U was x squared plus 1. So this becomes 5 times the quantity x squared plus 1 all to the fourth times 2x. Now, we're hoping that you'll get to the point where you do not need to necessarily do all of this side work to write out this template. But for now, today, I'm going to do that each time. Okay, so notice I needed two basic derivatives, the power rule to differentiate the fifth power function, and then multiple times with the power rule or constant rule to work out the derivative of x squared plus 1, and then we multiply it together. Okay? Now, the alternate way that this rule is written, but it means the same thing, is this version down here. Let's talk through the meaning of that one. If you can see your original expression as f of g of x, what I originally do is I ignore what's on the inside. Okay, I'm going to cover it up for a minute. Okay. So I just see it as f of something. And in my example, I would have been covering up the x squared plus 1. So all I see is something to the fifth. And so I can now think of this as, I was calling that box u to the fifth, or just something to the fifth. And so now that would be, no matter what my something is, the derivative of this is the basic power rule. I bring 5 down and then decrease the power by 1. Okay, so it'd be like me putting a box in here, and I've got 5 times something to the fourth. And we call that f of g of x. Okay, it'd be like me putting the box over here too. So the derivative of something to the fifth is the basic power rule, 5 times that something to the fourth. Okay, and then the second link, the second part of the chain rule is to uncover the box, and once I uncover it, put its derivative beside here. Okay, and so what I did there was the power rule first, 5 times something to the fourth, and that something is x squared plus 1. So at the end of the problem, it's 5 times x squared plus 1 to the fourth. Once I uncover that and write it in there, the derivative of that boxed expression has to be multiplied at the end. So the derivative of x squared plus 1 is 2x. Okay? So my goal today is to demonstrate this a number of times. And in all the ones we're going to try today, you should recognize that once I've boxed over, the inner part will end up with a power function as the primary differentiation rule. Okay, so that leads to what we call the general power rule. I want you to notice that on your list of derivatives, on the front side where you've been filling in all these special differentiation rules, one of the first ones was the basic power rule, where I'm going to write it under here. I think on your paper it's box number 2. That is the derivative of x to the n, such as like x squared or x to the 5. We bring the power down, and then as a coefficient, and then the power of x decreases by 1. Okay, so this would be something like this. The derivative of x to the 7 is 7x to the 6th. Now, today we're going to see all the examples will be such where it won't be x to the power of 7. It might be some other function to the power of 7. And so to formulate that in the light of the chain rule, we like to write the base of the power as u, where it's understood that u is just some other differentiable function. Okay, so it's understood that u is a function of x itself. And so now the chain rule application is I apply the power rule as usual. N comes down as a coefficient. The power decreases by 1. But then the chain rule states we must find the derivative of that inner expression and multiply it afterwards. Okay? So my application for the general power rule would go something like this. And I can even use something like the last example we had a minute ago. X squared plus 2 all to the 7 now. Okay, so my thinking is u is the expression x squared plus 2. Okay, so for a minute here, you could even use the little box method again. I could just cover this up for a minute. The boxed expression, I don't care what it is right now. The first link in the chain rule, or the general power rule, is to apply the power rule. 7 times something to the 6th. And that's something we were calling u. Okay, so now, and then we multiply by the derivative of what's under the box. So the last link in the last part of the problem is to uncover the box and replace it with x squared plus 2, and then multiply all of this times the derivative of x squared plus 2, which is just 2x. And now this could be my final answer to what the derivative is. Typically, I will bring together parts that can be combined. Like, I can't really bring anything into the parentheses, but anything that's outside that's being multiplied, I could combine together, such as 7 times 2x could be made into 14x. And then I'll just leave the power on its own there. So this would be my derivative. 14x times the quantity x squared plus 2 to the 6th. We're just going to practice applying this a couple other instances, and then you'll be ready to try about the first 8 or 9 problems on the assignment sheet. Okay, so here I've got y equals x squared plus 1 to the 3rd. Once again, I'm going to identify the inner part and call it u. And if it helps, just cover it up for a minute and don't worry about what that is. And so now that I've covered that up, all I see is it's a power function, something cubed. And so the first round of this differentiation is to apply the power rule, where something is in the box that we have not really cared about yet. Okay, but then once I know what that is, I have to multiply by the derivative of that. Okay, so maybe we could even say this. It's going to be 3 times something squared times the derivative of that something, right, the prime. So now wherever there's a box, I'm going to put x squared plus 1, but then if it's like this number prime, we take the derivative of this. So my derivative y prime is now 3 times the original inner expression squared times the derivative of x squared plus 1, which is 2x. So like in the previous one, let's combine the parts that are outside the parentheses. 2x times 3 is 6x. And then I've got x squared plus 1 squared. That would be my derivative. So if I wanted the slope, for example, of the original function, the slope of this function can be calculated with this formula down here. Okay, so this one I encourage you to try it on your own, but I'm going to write out the solution. I encourage you to pause the video and try this one, very similar problem again. I've got x squared minus 7x, but it's all to the 8. I encourage you to pause the video and try it, but I'm going to work it out in the meantime. I would let u, think of u as x squared minus 7x. So therefore I think of this as y equals u to the 8. And so for the general power rule, 8 u to the 7 times u prime, and then I've got to replace u and u prime. So y prime equals 8 times x squared minus 7x to the 6th, or 7th, sorry, times the derivative of x squared minus 7x, 2x minus 7. This time everything is kind of in parentheses, etc. So you can't bring anything inside of the 7th power without doing some extra work, but I could multiply all this times 8 if you wanted to, or you could just leave it 8, maybe put everything that's to the 1st power first, and then the 7th power second. Nothing wrong with this. This is all now nice and factored out. There's no reason to try and combine it all. So this would be our derivative. So the last two examples will be using this principle, but I will require you to rewrite the function first. So in a similar way to what we did before, if I had to find the derivative of 3 over x to the 5, your choices are either use the quotient rule, but to me that would not be working smarter, that would be working harder. Smarter would be to write the problem over again as the derivative of 3x to the minus 5. And this only requires the power rule. Okay, so we are going to do that with ours too. I'm going to rewrite this as y equals 3 times the quantity x plus 7 to the negative 5. And now I'm going to identify u to be the quantity x plus 7. So I can now, my thinking is, this is 3u to the negative 5. So now I see it in a more basic form, and I'm going to apply the general power rule. So y prime, I bring the power negative 5 down, multiply by 3, so negative 15. Decrease the power by 1. Be careful, negative 5 minus 1 is negative 6. And then we multiply by u's derivative. And then we just finish the problem by substituting back in terms of x. So y prime is going to be negative 15. U is x plus 7 to the minus 6. Now think, what's u prime? If u is x plus 7, u prime would just be 1. So I don't have to multiply by anything but 1, which doesn't change the problem at all. So I'm just going to not even write it and rewrite the answer as negative 15 over the quantity x plus 7 to the 6th. And there would be my derivative. Last one. Let's use a square root this time. Now, we could think of this as the power rule, because I could write, remember, we can write the square root of u is the same as u to the 1/2, right? Those are equivalent. But what I like to do instead is use one of our other basic derivative rules here. The derivative of square root x is a good one to memorize. It's 1 over 2 root x. Okay? So what I'm going to do here is I'm going to let u equal x squared plus 1. And I'm going to rewrite my problem as y equals the square root of u. So now I can apply the chain rule in a similar way to the other ones. To find the derivative, I apply the basic rule to this. The derivative of square root of u is 1 over 2 square root of u, similar to the basic rule above. But because u is not just x, u is another differentiable function, the chain rule says you got to multiply by u prime, the derivative of u. And now we will make a note of what that is, and all gets multiplying together. So y prime would be 1 over 2 times the square root of u, but let's put x squared plus 1 back in it now, times the derivative of u, which is 2x. Now let's write this as 2x over 1 so I can now combine the two fractions, right? The numerators are 1 times 2x, which would be 2x. The denominator is 2 of the square roots plus times 1. So we're just multiplying the two fractions together, multiplying the numerator, multiplying the denominator. And then the only obvious simplifying that's easy is noticing there's a 2 as a factor of both the numerator and denominator. So just get rid of those. So my simplest answer, I think, would just be this: x over the square root of x squared plus 1. Hope this helps you get started in assignment 2.4. You should just work on the first 8 or 9 problems for now, where they should all look like these that we've looked at in this video today. Have a great fall break, and we'll see you guys back here soon on next week.